assumptions from chapter 7 and then start the next chapter. I hope you're getting used to probability trees and how they can be used to do, find probabilities of events where one thing is connected to the other kind of thing, or do two things at once. Then you're trying to keep track of all the ways it could happen and the probabilities of those ways. So what I've got here is a version of question 9. This is a kind of condensed version of what it says. There's a class with 30 students in it. 5 are left-handed, and you pick 2 students. Now, they don't say without replacement, but if you're picking 2 students, would you agree, if you pick a student, you're not going to say, oh, you're left-handed, and then they go back and join the class and you try it again. So I think in context, you can assume that when it's you pick 2 things, unless they say otherwise, you should assume that it means without replacement, right? If they wanted it to be, the person went back to the class and you could pick them again, which is called with replacement, they would tell you. So if you're wondering, is it with or is it without, work on the assumption that it's always without replacement unless they tell you otherwise. So 30 students, 5 are left-handed. We're going to pick 2 students, and we are going to do one of those probability trees. So we'll start here. And the first thing is going to be my first student. And that student could be left-handed, or I guess I could call them not left-handed, but that's just right-handed. Now, what do I know about the first pick? Well, since 5 of them are left-handed, that makes 5 out of 30 students is the chance that I choose a left-handed, and that means the rest, 25 out of 30. Now, you notice they only told me how many left-handed, but it was pretty obvious how many of the other group there were. These 2 trees, these 2 branches of the trees should always add up to 1. So if you tell me this is 10, I know that's 20, right? If you tell me this is 15, I know that's 15. So that's the first branch done, and we're only doing 2. So we'll do the second now. And that second student could be left-handed, or they could be right-handed, or they could be left-handed, or finally, they could be right-handed. Let's see what we've got. Let's do this student here. If you follow the tree backwards, a left-handed student has already been picked. So when you get to this student, there's only 29 students in the class, right? This person's already standing at the front. 29 students at the front. And how many of them are left-handed?
Now there's 4 of them, right?
Yeah. Now, if you know this answer, can't you figure out this one? Because it's also going to be 29 students, but won't it be the rest? So 4 and 25. Now, if we do this left-handed student, what do we know about them? Well, we know that this has already happened, right? There's a right-handed student being chosen. So there's only 29 students, but 5 of them, right? Because that was a right-handed, so all the 5 left-handed students are still there. There's 5 of them, and that makes this fella here the rest. Are we getting a little bit more comfortable how to build these trees up? Now, what's going to happen to finish this is that we're going to get the probabilities of each of the 4 events. And you just basically multiply the pathway. So 5 out of 30 times 4 out of 29. And that becomes 20 out of 30 times 29. That comes and in fact, what I should have done, now that I've thought about it, I will. You want to make this fraction as simple as possible. I can look at that and know how to simplify it, but why don't I just get the calculator to do it? So from the start, 5 out of 30 times 4 out of 29. Hit the math button, option 1, fraction, there. So the final probability of that is 2 out of 87. Right, if I go through the others, then it's going to be 5 out of 30. What's that? 5 out of 30 times 25 out of 29. And the answer I get is 25 1/74. Third one, 25 out of 30 times 5 out of 29. And that ends up being 25 out of 174 as well. And the last one is 25 out of 30 times 24 out of 29. And the calculator gives me that as 20/29. Technically speaking, if I took all 4 of these, shouldn't they add up to 1? I'm not going to, because I'm pretty sure I did it right. Now, in this question, that's all you're being asked to do. But can you imagine there was a question where they wanted you to do something a little bit like make a table, and you'd have first pick and then the second pick. First pick could be left or right-handed, and the second pick could be left or right-handed. So what would go here would be the left and left, which would be 2/87. Then a left and a right, which would be 25 1/74s, 25 out of 174, and finally 20/29. So you might take this and build a table. I mean, they don't ask you to do it all the time, but sometimes they do. Are you comfortable that you can use these numbers to fill in a table? And that is the end of that tree diagram, which was essentially question 9. So this is our final tree diagram. I've already got it partially set up. It's a version of question 14, so I'm going to have to look at what 14 says. Right, you can't see it, but I'm reading it. Suppose that only 3% of individuals have a disease, right? So 3% of the population have a certain disease. How many, I guess you could say, don't have the disease? I've just called it healthy, right? They may have another disease, but they don't have that one, right? So the healthy group, what number goes here? What's the chance that you choose somebody who's healthy, who doesn't have the disease?
0.97.
And for those who are unsure, could you tell us where you got it from, Mark?
Just subtracted the 0.03 from 1.
Right. So if you know either one of these 2 branches, don't you always get the other one for free? If I tell you that's 0.7, this is 0.3. Because when you read these stories, they're almost like a lawyer wrote the document. You know, well, here's I'm reading this straight out from the thing. If an individual has a disease, the probability is 0.96. No, read on a bit. If an individual does not have the disease, the probability is 0.6 that they test falsely. Oh God, look at that. If an individual does not have the disease, the probability that they test falsely, right, that's a negative test, is 0.06. And if they do have the disease, the probability that they test correctly is 0.96. So when I'll read that second one, this one again, because God, even after I've written it, it's unsure what I've said. If an individual does not have the disease, the probability is 0.06 that they test falsely. You see, so I'm calling it test positive and negative, right? Test positive, right? Test negative. So you put this package together. Won't this be 0.04? And won't this be 0.94? Are you happy about they only told me 2, but I figured out who the other 2 were? So you read the story and you get, the split that goes here, and then they tell you one of these, so you get that, and they tell you one of these, so you got that. So when you're finished, all the pathways should have a probability on them. Now, in this case, you are going to create one of these tables. And so let's get the numbers going. If you want to test positive, you multiply 0.03 with 0.96. Oh, your backslash. And you get 0.0288. And if you go this way, 0.03 times 0.04, you get 0.0012. And if you go this way, you get 0.97 times 0.94. And this is 0.9118. And if you go the last way, it's 0.97 times 0.06, and you get 0.0582. I hope they're right. If I had time, wouldn't I just add them up and make sure it came to 1? That would be a good check. Right, you build this table. Those who have the disease, darn it in space. I can fix this. There's the ones that have the disease. No, that's fine. My wife came in and I'm blaming her. She distracted me. Because I may have got my plus and minuses mixed up. Let's see. Oh no, that's right. Okay. So the numbers are fine. I just got confused. So leave them alone. Everything's cool. So what's this? Have the disease and test positive 0.0288. Have the disease and test negative is 0.0012. Healthy, that's the one I made a mistake on. That's 0.06 and that's 0.94. There we go. So I did actually make a mistake here. That then is that you're healthy and you test positive. Healthy and you're healthy and you should test negative. Okay. I want the big one and the little one to go in the right places. So if you're healthy, you should test negative, right? So that's 0.9118. And the other one is 0.0582. It shouldn't be as hard as that, but I'm just distracted. If you're healthy, shouldn't you test negative for the thing? And if you're healthy, you shouldn't really test positive very often. So test negative, test positive. So there's your guy. Now, if you want to know what's the probability that you have the disease given that you test positive, given that you test positive, it's those two. So if you add those up, what do you get? You get 0.0288 plus 0.0582. So on the bottom, you get 0.087. And have the disease is 0.0288. So you take that guy and divide it by the total. So that's the probability that given that you're test positive, so you use this rule, have the disease out of the total that's there. Have the disease out of the total. So 0.0288 divided by 0.087, and we get about 0.33. And as I said, that is a lot easier to do than kind of what I made it to be. Okay, are we good with that one? I think the first one went smoother than the second, but they're all kind of the same after a while. So what's left? I said there were 4 questions to do. There are 2 where you do not need to, and it's probably a good idea not to, do a tree diagram, even although they look like they might be. And you could certainly do them that way, but there's a quicker way to do it. Suppose you're playing a gambling game and the chance that you win is 0.4, right? So you win about 40% of the time you play. Maybe it's blackjack. And it's independent of each game. That's important. It means if I won my first game, the chance that I win when I play it again is still 40%, still 0.4. Now you play 4 games in a row, find the probability that you win at least once. Now, if you try and do that with a tree diagram, can you trust me, it would be from left to right and it would be huge, right? Because 2 on the first split, 4 on the second, 8 on the third, there'd be 16 guys at the end, and it could work that way. But we're going to do a little cheat. We are going to find the complement of the event. Now, to remind you, the complement is the exact opposite of the thing that you're looking at. So we're looking at right now the probability of winning at least once. What's the complement of that event? What's the exact opposite of winning at least once? That means you win 1, 2, or 3, or even 4 games. What's the opposite of that?
Winning every game but one. So 3 out of 4, right?
Okay, nope. I know what you're doing. Try again.
Probability of losing?
Yes, all of them. If one event is you win at least once, then if you win at least once, now we're talking out of 4, right? Then what could happen? Well, you could win, right, exactly once, right? 1 out of the 4. Couldn't you also win 2 games out of the 4, 3 games out of the 4, or all 4 games out of the 4? Wouldn't that be the equivalent of winning at least once? Now, what's the opposite of that? Well, isn't that not winning any? Okay. So the complement of winning at least once is losing all 4 times. Does that work? Now you might say, well, all you've done is change that probability into this one, which is true. Isn't there a rule that says, if you take this guy and you find this one instead, isn't this probability just 1 take away its complement? Now you might think, well, I've got a different problem, but I've still got a problem. Well, this one's much easier to calculate because it's the probability that you lose, 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 and lose, right? And isn't that only going to happen one way? So I don't need to figure out all the different permutations of winning 2 games, 3 games, 4 games, 1 game. That would take forever. Isn't this much easier because there's only one event, and that is you lose, 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 and lose. And we know that you can do this by just multiplying the probability that you lose together 4 times. Remember that? If you do 4 events and they're independent, you can just multiply them. Now, there's only one number missing here. What is the probability that you lose?
0.6.
And that's because of this guy. So what we have is 1 takeaway 0.6 times 0.6 times 0.6 times 0.6, which can be written down as 0.6 to the power of 4. And then the calculator takes over and we're finished. 1 take away 0.6 to the power of 4 comes out to be 0.8704. Sneaky. So sometimes it's easier to find the complement of an event and subtract it from 1 to find the guy that you're looking for. Would you agree that's a lot less work than building a table where there was 4 levels and by the time you got to the end there were 16 things going on and then you had to add them all up and all sorts of things that could go wrong? And our last question is the same kind of story. This waitress has discovered through experience that the probability that she gets a large tip from a table is about 0.26. And she describes what a large tip is, but it doesn't matter. So 0.26, about a quarter of the time she gets a decent sized tip. And it's independent of each table that she serves. That keyword is independent. She serves 5 tables one night. Find the probability that she gets at least 1 large tip. Do you see that phrase, at least 1, is a clue that it's just the same as the one we did a minute ago? So I'm going to do the complement. So the probability of what we're looking for is 1 take away the complement. And at least 1 is the same as getting no big tips. No, I guess I should stick to the phrase, no large tips out of 5 tables. Well, that's not getting a large tip, not getting a large tip, 3rd time, 4th time, 5th time. Agreed? 5 times in a row, she doesn't get a good tip. And that becomes the probability of not getting a large tip multiplied together 5 times. What is the probability that she doesn't get a large tip?
0.74.
And you got that by just taking that away from 1, right? And since there's 1, 2, 3, 4, 5 of these, can't we do that? Make the calculations quicker. And so we now have 1 take away 0.74 raised to the power of 5. And the answer that you're going to get is 0.7. Let's say it's to 2 decimal places. Actually, it says 4, so I'll correct myself there. So there's a 78% chance that she won't get a decent tip. Now, I've done various jobs when I was a student. I've never worked in restaurants as a waiter or anything, so I can't speak for that. But if any of you have, do you just get one of those nights where nobody gives you a decent tip? And it's not anything you've done, it's just the people you get. You know, it happens. According to this poor woman, isn't that going to happen about 3/4 of the time? Right. Kind of unhappy about that, but are we comfortable with those last 2 probabilities that you don't need a tree, you just use the complement to get around a thing? And you know that you're going to do it this shortcut way because the phrase is going to be at least 1 blah, 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 right? So the minute you see the at least 1 part, think of question 13 and the one before that, question 11.
So I have a question real quick.
Yes, Tanya.
Is the probability that at least 1 large tip 78% or is it 22%?
The probability at least 1 large tip is is that one. Oh, okay, 3/4 of the time she's going to get a large tip. So 25% of the time she's not. This is the question we've been asked to find the probability of. So it's this guy up here.
Okay, thank you.
So this is the 0.78. Because I did one, did I do one takeaway? Yeah, I did. The calculation I did was the whole thing. One takeaway, that. Are we good? Right. New chapter. Oh, what's the difference between a Canadian and a canoe? Anybody know? What's the difference between a Canadian and a canoe?
No, what is it?
Canoes can tip. Don't you shake your head. That was a good joke. Autumn, was that a good joke?
It's not your best one, but it was good.
Okay. I didn't know I was getting graded. I hope you grade me on a curve. So we're going to look at, well, the heading is called Introduction to Random Variables, but what we're really focusing on in chapter 8 is a table that is called the probability distribution table. What you do in these stories is, can you imagine that you're looking at an event and you write down all the possible things that could happen and the probabilities of all those things happening? That's called the probability distribution table. Right. So imagine that I had what will I pick? Suppose I did a very simplified version of the number of children in families. So I went to America and I collected data on this and I found the probability of it happening. So there was 0, there was 1, there was 2, and then there was 3 or more, right? So I'm counting the last category as 3, 4, 5, 10 children. And we went out there and we collected data and it ended up being 0.3, 0.4, 0.2, and finally 0.1. That is an example of a probability distribution table. Now, if I did this correctly, shouldn't they all add up to 1? Because I basically, isn't this everything that could happen? You can't have 2.5 children, right, or whatever, right? That's what 1 looks like. Now, if you are given, strangely enough, there's only a few questions in this section. If you are given a table and there's a missing term, you should be able to figure out who's missing. So just duplicating the table that they've got. There's a guy called K, and then there's the probability that your thing is equal to K, and K takes numbers 1, 3, 6, and 8. So evidently that's the only 4 numbers that can happen. I have no idea what the story would be, but it doesn't matter. The chance that you get a 1 is an 1/8. The chance that you get a 3 is an 1/8. And the chance that you get a 6 is an 1/8. And your question is, what needs to go there? Would you agree that's, yeah, would you agree it's pretty much look at what you've got and see what's missing? Well, I've got 3/8, so doesn't that really just mean 5/8? Now, isn't that going to be nice when you get a question where that's all you need to do and you don't need to spend 20 minutes building a tree? I think that's kind of nice. Now, let's suppose you were given a completed probability distribution table. So this is a bit like question 3 now. The one that we just did here is like 1 and 2, right? And this one is births again. And probability of it happening. And this is births in a hospital. So some days there is not one baby born. And then 1, 2, 3, what did they get up to? 7, 4, 5, 6, 7. That's fine. And I have 0.1, 13, 28, 24, 17, 5, 2, and a 1. Evidently, they never get 8 births in a day. It never happened. And you could be asked, half the battle is understanding the notation. Find the probability that x is less than or equal to 3. X is basically those guys. So if you wanted to turn this into English, it would be something like, what's the probability that the number of births is less than or equal to 3? Does it make more sense when you put number of births down than x? I mean, it's easy to understand what you're doing. So what are you going to do to calculate that probability? I want to know the chances that tomorrow that the number of births in this hospital is 3 or less. What would the calculation be?
1 minus 0.24.
Oh, you're thinking like the at least carry on from the other questions? I see where you, yeah, I'm seeing where you're coming. Right, look at it a different way. If I say number of births less than or equal to 3, how many am I talking about? Am I talking about 3? Yeah. Am I talking about 2 as well? Yeah, it's possible. 1 and 0. So when you look at this, can you see you're talking about those events there? The one less than thing would happen if you were looking at that and would it be much easier to just calculate that, right? That would be the situation you're thinking of. So back to what I was saying. What do you do then to find this probability? Here's the numbers. What do you do with them?
Add them all up and
That's it.
subtract from 1.
No, not even this. No, just add them up. We've still got that at least thing in our head, right? That's a special case for those situations. This is not one of those situations. So you add up all the ones that represent this event. So in this case, that's 23, 43, 51, 71, 75, I believe. Now, the next question says, explain what does 1 take away the probability x less than or equal to 3. Who are you counting now? And what probability are you getting from that?
greater than or equal to 4 births, so
Yeah.
25.
So anything that's not that one, right? And not that one would be all those, wouldn't it? Now, do you see in this case, it's not multiply, 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 right? That was like 10 minutes ago, right? Isn't this just picking the guys from the table, right? What would this one, I don't need to know the number, but what would this one be? How many births would that be? What types of births? I'm trying to phrase it different ways. If I asked you to find the probability that tomorrow this hospital had this happen, how many births would that be? I know this is an algebra system. Do you recognize that as meaning between 1 and 3? So between 1 and 3, wouldn't it be those 3 guys? So you could have a less than, I could do this one. Now I'm thinking about it. How many babies would need to be born for this event? What would the numbers be this time?
Five, 6, and 7.
That's it. So if you have one of these tables, couldn't you change that to anything you like? That's why X is kind of helpful. And you could find less than something, bigger than something, between 2 numbers, 1 minus something. Isn't there all sorts of combinations that you could have? Because all the probabilities are here, and it's just a matter of picking the ones that each event represents. So X less than or equal to 3 is all those guys. So you add up these probabilities. If you want between 1 and 3, you add up these probabilities. If you want greater than or equal to 5, you add these probabilities. So it's all about adding things together, right? So probability distribution tables, you typically add things in the table together. Now the next one is about, well, it's basically question 4. And we are going to do 3 coins. And we are going to build a probability tree, a probability distribution, I should say, for X. Let's get these right. What's X going to be? X is the number of tails. And then this is going to be probability that X equals K. That's just the way they write it. So if you do it, you could have, right, 3 coins and you throw them in there and you don't get any tails. You might get 1 tail, you might get 2 tails, and you might get 3 tails. And I'll put a total in to make sure I got it right. Okay, so you're throwing 3 coins. You agree these coins are independent of each other, right? Now I'm going to have to build a little, there's more than one way to do this, but I'm going to do it this way. Heads, tails, heads, tails, heads, tails. This is why tree diagrams kind of don't work very well. Yeah, I think I just about did it. Do you see how ugly it is by the time you do 3 things? Right. But I think I could just get away with it. If you said 4 coins, I would do it a totally different way. Right. So every single one of these little branches, we would put in its probability. But when you throw a coin, isn't the chance that there is a head or a tail, aren't they all 0.5? And it doesn't really matter whether it's the last coin that I throw or the second coin I throw, aren't they all 0.5? So I'm not going to even write any more 0.5s because every single one of these is the same number, right? They're all 0.5. Now, if you do 3 heads, that's 0.5, 0.5 times 0.5. And getting 3 heads is 0.5 to the power of 3 is a 0.125. I'm just checking. If they wanted fractions, that would be an 1/8. Okay. Getting 3 heads is the same thing as no tails. Now, it gets a little bit trickier. One tail. Would you agree that guy there is 1 tail? Is there any other places where you end up getting 1 tail? 1 tail means you're getting 2 heads as well, right? So 1 tail and 2 heads. Is there any other places where that happens? All right, which one do you see, Mark?
The third one down.
Great. A head, tail, head, isn't that 1 tail? Is there any other place? Because I can see one more.
Fifth one down.
A tail, a head, and a head. Right. Now, see each one of these, can you trust me that they're all 0.125 because you get them by a half, a half, a half. So that means I'm going to have 3 lots of that. Right, so you take these together and you're going to get 0.53. You're going to get 0.375. If I went through it, this would be 0.375. And if I finally did tails, tails, and tails, I would get 0.125. And the whole thing adds up to 1. So I know I've done it correctly. So I've created a probability distribution table for throwing 3 coins in the air. And it looks like that. Now, there is another way, if you don't like that tree, and it goes like this. So let me show you a second way of creating this tree. We find a sampling space. Well, you could have 3 heads, right? You could have 2 heads and a tail that can happen this way. You agree that's 3 different ways 2 heads and a tail can happen. Now, if you do 2 tails and a head, it could happen that way. And if you write down 3 tails happening, it could happen that way. Can you see the 8 possible events that can now happen when you throw, right, 3 coins? Aren't all of those events equally likely? Now, if you want to know 0 again, that's this one. It's 1 out of 8. How about getting 1 tail? There's 3 ways that can happen. 3 out of 8. 2, this way. 3 out of 8 ways of that happening. All of them being tails, 1 out of the 8, and that adds up to 1. Do you see that you get the same result? Do you like this way better than that? You don't care? They're both about the same? Yeah. Both work. Pick whatever one works for you. Right? I do not like doing tree diagrams for more than 3 things. So if it was 4 things, I would be doing one of these tables. Are we good? Right. Next one is a probability distribution table again. And we have a guy here called X and the probability of it happening. And the numbers are 2, 3, 4, 5, and 6. And the probabilities are 1/9, 2/9, 3/9, 2/9, and 1/9. And we're being asked to find what's the probability that you get an even number. That's those, isn't it? And what do you do with them? You add them together. So there's a 1 in 9 chance of that happening, plus a 3 out of 9 chance of that version happening, and a 1 out of 9, and there's the answer, 5/9. Couldn't I ask you what's the well, let's actually do it. If I went and said to you, what's the probability that you get an odd number? Who would you be using for that one?
3 and 5.
Okay, and 3 happens that many times, and 5 happens that many times, and 4/9. Or couldn't I just say it's a complement of that, and that's 4/9? Could you be asked to find the probability that x is greater than or equal to 5? Now, if you were asked that, who would you be adding this time?
2 9ths and 1 9th,
Okay.
or 5 and 6.
Yeah, 5 and 6, you're right. You could be asked that, couldn't you? Wouldn't it be those 3 guys? So what would that be? It would be 1/9, 2/9, and 3/9. That ends up being 6/9, so that's 2/3. And so I've done every possible combination that I can think of. Can you also be asked that? Okay, who would you add to get that last probability? What would it be?
3, 4, and 5. So 7 9ths.
Yep. So 3, 4, and 5. There's the chances of getting a 3. There's the chances of getting a 4. There's a chance of getting a 5. And I believe that adds up to 7/9. Are we getting more comfortable with probability distribution tables? They basically just take everything that could happen in this world. These are the only things that can happen. And they tell you the probabilities of them. And then the types of things you're asked are from this table, you know, find some other probabilities. Now, you might, no, we won't. Okay, we almost got it. There are only 2 more questions.